Well, hello, ladies and gentlemen. This is Mr. Kinney here. I'm going to go over the odd questions on our test review. So, what is the charge on an aluminum ion? Oh, of course, I don't have my... There we go, periodic table. Well, first off, aluminum lives right here in group 13, which means aluminum has 3 valence electrons. So when it comes down to any question on charges, if you're not sure, come back, draw your Lewis structure, and put the dots there. So aluminum has 3 valence electrons, and since it's a metal, metals will throw away their electrons because they have relatively few valence electrons. When they throw those few away, their next lower energy level, their next shell, is now totally full, and because each of those electrons they throw off is a minus charge, the ion that you get is going to be aluminum plus 3 ion. Now we tend to draw the brackets around to show this is a modified Lewis structure. The next lowest energy level, the next shell, would have a full set of 8. It has satisfied the it does this because it wants to satisfy the octet rule, which is to have electron configuration of a noble gas. Number 3, how many electrons does barium? Barium is Ba. It is located on your periodic table right here. How many electrons does barium have to give up achieving noble gas electron configuration? Well, first off, noble gases, they have satisfied the octet rule. They've got all 8 electrons organized in a pair, a pair, a pair, and a pair. The only exception is helium. Helium only needs 2 of those. We won't give you the exceptions. So, how many electrons does barium need to give up? Barium is in group 2 of the periodic table, so it has 2 valence electrons, like that. Not the best Lewis structure, but sorry, I squeezed in. So barium, because it is a metal, it is going to throw away those 2 negative charges. And now that it throws that away, it's no longer a neutral atom. It has fewer electrons than protons, and since it's a metal, it will become barium 2 plus ion. We can put a square bracket saying that's its new Lewis structure, because that tells us it's lost 2 electrons because it has a plus charge, but now it thinks it's a noble gas because its next lower shell has 8 valence electrons in it. How does an ionic bond occur? An element like lithium, a metal, if it teams up with a nonmetal, and the perfect nonmetal is chlorine, they have 7 valence electrons, so we would draw its Lewis structure like this. This lithium will throw away, metals throw away their electrons, so when it throws away the electron, that lithium becomes a plus 1 ion because it's lost its 1 charge. Chlorine now has gained Cl. Let me draw the electron configuration as we had it before. I'm going to make, instead of a dot, I'm going to put a negative sign. That chlorine now has 1 extra negative charge. It's a minus 1 ion. And together, this minus 1 and that positive, they're going to attract together. Electrostatic, E-L-E-C, electrostatic force pulls them together. And make sure you've got that written in your summary page. That's a biggie. That's the strongest force in chemistry. Well, okay, other than the strong force in the nucleus. But anyway, it's in bonding, it's the strongest force we've got. So, how does an ionic bond occur? When a metal ionizes and forms up with a nonmetal, which also ionizes. It takes a metal and a nonmetal, and they are, one is giving electrons, the other is taking. Oh, shoot, I did the wrong one. Dang it. Oh, I was supposed to do number 5. How many electrons does nitrogen gain? Nitrogen, doggone it. Sorry, that was a beautiful answer, but the wrong question. All right, nitrogen has 5 valence electrons because it is in group 15. And what it's going to have to do, nitrogen needs to gain 3 more. Nonmetals need to gain electrons to become stable. I've drawn the dots here as a negative, negative, and negative. So what happens is when nitrogen, a nonmetal, takes some of these electrons that the metals are throwing away, it will become a minus 3 ion. So it's going to tend to attract, very often nitrogen will attract hydrogens, because hydrogens are a +1 ion, and they'll come over and they'll team up with it. But how many electrons does nitrogen gain in order, since it's a -3, okay, what we started off, it's like this, it needs 3 more electrons. So that becomes -3. And once it has this, nitrogen now thinks it is neon. It thinks it's a noble gas. All right, let's do the correct one this time. 7. How many valence electrons are transferred from potassium? K has 1 dot. It's in group 1 of the periodic table. To nitrogen, okay, we've got nitrogen, 1, 2, 3, 4. This time I'm going to draw the paired share over there. How many valence electrons are transferred from the potassium atom to nitrogen in the formation of potassium nitride? Well, each potassium is going to give 1 electron. But in order for this to work, you need to have 3 potassiums over here working to give their electron, because each of those potassiums will give their electron over here. And what you end up with, if we were to draw the Lewis structure, so this nitrogen will now have the octet rule satisfied, but since it gained those 3, it's got a -3 charge, but it's going to be surrounded by 3 potassiums with a +1 charge. And these 3 potassiums with their +1 charge, all 3 of those plus charges perfectly neutralize this. Atoms share electrons to become stable, and this way all of these negative oxidation numbers, these ionic charges, cancel each other out. Number 9, what is the formula when Na+1, okay, this is crisscross, +1, and nitride, Na3-, well, you're doing crisscross, so rewrite NaN. I'm going to bring that, now that -3 becomes a subscript. We have 3 sodiums now and just 1 nitrogen, which, okay, nitrogens have a -3 charge. If you bring in hydrogens, kind of act like lithium here, where they're going to be, or like potassium was here, they're going to give up their 1 electron. So this is the new compound. Na3, you don't have to bother to put the 1, but you can do that to help you out. Number 11, am I still on the board up there? What is the formula when Na+ ion and sulfate? Now this threw a lot of you today. Sulfate, let's put a parenthesis around it, 3-. Now at this point, let's just assume this element, because we got the bracket, this is a polyatomic ion, this is just the element SO. Don't worry about the 4 or anything. Now you just do crisscross. NaSO4, that crisscrosses down to there. That +1 crisscrosses to there. You actually don't even need it. Na3SO4. Number 13, ionic compounds are normally in which physical state at room temperature? The most classic ionic compound is table salt. And it is a solid. Actually, I'll say a brittle solid. Ionic compounds basically are rocks, brittle solid. So when you look at the characteristic of rocks, they tend to have some type of metals in them and a non-metal. They're basically rocks, is what most ionic compound are rocks, so they're brittle solids at room temperature. Let's see, number 15, what force holds ionic bonds together? Well, that's coming back up here. I told you on number 5, it's the electrostatic force. That was in your notes. So ionic bonds, let's say you've got your lithium +1 ion bonding to a chlorine -1. That plus charge is drawn to that negative charge. It is one of the strongest it's the strongest force in bonding chemistry, not talking about nuclear stuff going on. So this is electrostatic. What that means is you got these electric charges, but they're drawn next to each other, and then once they get together, they stick together and they don't move anymore. That's the static part. Electricity, static. Electrostatic force is strongest force in bonding regular chemistry. Number 17, why do atoms share electrons in covalent bonds? Well, metals throw away electrons, nonmetals, covalent bonds are nonmetals bonded to nonmetals. And nonmetals cannot throw away their bonds. So if we're going to get two nonmetals, let's just get our friend, we'll make it kind of easy. Let's do fluorine. Uh-oh, forgot where I was. So fluorine, for example, it's a nonmetal. 1, 2, 3, 4, 5, 6, 7 valence electrons. Well, it's not going to, if there's not a metal around to give it an electron, fluorine will actually, believe this, it will actually share its electron with another fluorine. That is a covalent bond. We've got a pair of electrons being shared there. Let's try another one. And then actually this can be good for the Lewis dot structure for O2. Let's draw oxygen. It is in group 16. Now I'm going to put the paired electrons that are paired up and happy off to one side. Now since we got to do two of them there, I'm going to draw the mirror image of this like that. The two paired electrons there. So now what happens, those pair team up and that teams up. And we end up getting, I'm going to kind of clean this up. The chemist would tend to just draw it like that. But they know that oxygen has these two pairs each of these spinning electrons that are happy. And so that's what this would look like. So that's a single bond. There's 4 electrons. And if you need to, and you see those dashed lines, draw dots. Oxygen here had 4 electrons, or a double bond. Okay. Let's see, do we have any more? Oh, let's just do one more because let's do our friend. Oh, let's do nitrogen. Oh, N2. Okay, I'm going to jump to N2. Chlorine is going to be just like that one. Nitrogen, 1, 2, 3, 4, 5 valence electrons. 1, 2, 3, 4, 5. I'm putting the paired as far away. And look at here now. Nitrogen will team up that one, this one, and that one. We did that in class today. That is a triple bond. It takes a lot of energy to make a triple bond, and it gives up. Oh, sorry, I was off the page. Sorry about that. And it gives up a lot of energy when you eventually break it. All right, so they share. Why do they share? To achieve noble gas electron configuration, to become stable. To be stable, which is going back, another way to say to be stable is to have noble gas electron configuration. They satisfy the octet rule. They all want, almost all the atoms want 8 electrons in their outer shell. Helium, hydrogen, lithium, and beryllium, maybe boron, they'll, okay, anyway, don't want to confuse you. 19, which of the following represents an ionic compound? Well, according to your notes here, metal to nonmetal is an ionic compound. Nonmetal, nonmetal. Nonmetal, nonmetal. Those are covalent. Metal, nonmetal. This is ionic. Those are covalent. And let's see, that is nonmetal and nonmetal, covalent. 21, molecular compounds. Okay, that's covalent. Are made from bonding. Covalent, nonmetal to nonmetal. Non-metal to, now I sure hope you can see that. I don't have anybody here to say, hey, we can't see that. Non-metal to non-metal, M-E-T, that's supposed to mean L. Oh well, sorry. 23. Covalent bonds are made between which two types of elements? Well, we just talked about that, nonmetals. They are sharing their electrons because nonmetals do not throw away electrons. They only want to take them. And if they cannot take one from a metal, they will share them, as we talked about before. Nonmetal to nonmetal squared. How do you like that? 2 nonmetals. Metals form blank ions. Okay, metals like lithium, they have 1 valence electron. They're going to throw that away. They become positive ions or cations. See, that positive is like a cation. Nonmetals form negative ions. For example, fluorine here, used it before. When it gains 1 more electron, it becomes a negative ion, which is known as an anion, if we ask you the actual terms here. So cations and anions. Metals give away electrons to become positive. Nonmetals take electrons. List the characteristics, including melting. Oh, come on. Seriously? Okay. Melting point. All right. Covalent compounds. We're going to find out in our lab here really low melting points. I mean, imagine you put a piece of wood in the Bunsen burner. It's going to start, well, it'll probably burn before it melts, but a piece of rubber, you put it in a Bunsen burner, it's going to begin to melt. Wax, same thing, it'll smelt. Conductivity, low or no. Actually, I'm going to basically say no conductivity. We found that in our conductivity lab. Covalent compounds tend to be, let's see, brittleness. No, they tend to be bendable. Ionic compounds have very high melting points. You'll find out. You're gonna melt some salt, or maybe you already have when you're watching this, and it takes a lot of energy to try to melt it. Covalent compounds, almost immediately. Conductivity, we found out that ionic compounds, we had them dissolved, they had very high conductivity. In our lab, we had, I think it was vinegar. Yeah, we had vinegar in our lab. We had salt water. And then we had, I think, baking soda water. Those were all very conductive. Ionic compounds, very brittle. Basically, ionic compounds are rocks. Number 29, describe the bonds between molecules and solids. Hey, solids are locked into a rigid pattern, and it takes a lot of energy to do that. So if you want to melt them, you've got to add a lot of energy to them. So liquids, they're close together, but they're freely moving. So they're really close together. Usually it needs a little bit higher pressures, because if you get a gas, which are really far apart, okay, if you add more energy and squeeze these together, you can turn them into a liquid. But gases, they have very weak bonds holding them together, so they tend to fly apart. Solids it takes a lot of energy, strong bonds in a solid, weak bonds, weakest in a gas, because there's nothing holding, they're flying apart. All right, what electrons have these electron configurations? So, okay, that kind of, number 31 through, everybody. So first off, neon. So when you see this little square bracket, that means you need to first find out the electron configuration of neon and then add on this one here. Well, neon has 10 electrons, and so there's 10 electrons over here. This is just a shortcut. Chemists are lazy. They don't always want to write out the full electron configuration, so they'll just say neon's electron configuration plus a 3s1. So what that's going to be is, what elements have this 10 electrons plus 1? 10 electrons plus 1 is sodium. That's going to be Na, because sodium has 11 total electrons. Neon has 10 electrons plus this 1 and the 3s, 11 electrons total. Okay, this one over here, neon has 10 electrons. Chemists are too lazy to write the 1s2, 2s2, 2p6. They're just going to put neon. We've got plus 2 more electrons in the 2s, plus 3p5. Okay, so I'm pretty sure 1, 2, 3, 4, 5. I think this is chlorine. Let's see if those all add up to 17. Yeah, 10 plus 2 is 12, plus 5 equals 17 total electrons. And if you have 17 electrons, you are the element chlorine. What families are S1? Okay, S1. So if you have the electron configuration, we're working with electron configurations. Let me come over here, show that to you. This is in your packet. We've been working with these. Okay, sorry for the, there we go. This one right here. Okay, all of these elements, S1, if an electron configuration for any element, no matter how big, if it ends in either S1 or S2, whether it's, maybe it's 5s2, 4s1, if it's an S, these all end up being, these are going, S1, okay, that would be 1 electron in their outer shell, and that would be the alkali metals. So on your periodic table, This is called the S block. So any atom that ends in S1 is going to be one of these over here, the alkali metals. Okay, a P5. All right, this is the P block of the periodic table over here. You can see right over here. And if it's a P5, okay, let's see. 1, 2, 3, 4, 5. Okay, it's going to be this group right next to the noble gases. That's the halogens. So anytime you do the electron configuration for a halogen, it's going to end in P5. All right, P6. Okay, well, that's going to be right over here. P, 1, 2, 3, 4, 5, 6. That's going to be a noble gas. If you do the electron configuration for any noble gas other than helium, because it's too small, it's going to end in a P6. Like for neon, it'll be 1s2, 2s2, 2p6. All right, 30. Oh, dang it, I did the wrong problem again. Okay, well, you got a little bit more. Let's see, what elements should these be, these electron configurations? 2, 4, 6, 7. There's 7 electrons total. You look on your periodic table, 7 electrons is going to be nitrogen. Okay, over here, 1s2, 2s2, 2p4, 2, 4, 6, 8, 8 electrons. And that's going to be oxygen. Has 8 electrons. And let's see, coming over here, we have 2, 4, 6, 8, 9 electrons. Let me make sure 5 plus 9, yeah, 9 electrons. And that's going to be our friend fluorine. All right, what are valence electrons? They are electrons in your outer shell. Outer shell electrons. That's what they are. And that's what's the primary thing for governing how elements form. Almost done, thank goodness. This is going long. 37. Oh, this was weird. Cations. Okay, cations are positive ions. This kind of was worded weird. While blank electron. What? Blank electron. Cations. Maybe they're going to say, yeah, this is stupid. Whoever did that needs to learn to, they need to talk to an English teacher. Metals lose electrons and they become cations, positive ions. Nonmetals, okay, they will gain, they'll love to take that electron. They gain electrons to become anions with a negative charge. So that's what this is getting here. And give an example. Okay, we've done it already. Cation example. Okay, lithium plus 1 ion. Or iron plus 3 ion. Over here, nitrogen is pretty notorious for being a -3, and oxygen is the most famous of the negative ions over there. So there's that. Finally, whoa, I'm done almost. Describe the periodic trend for electronegativity and how it relates to bonding. Well, first off, bonding, electronegativity, that's going to tell us whether the compound is a polar molecule. The differences in their electronegativity. That's this chart. Tells us the electronegativities. Now look, when you look at this chart, as you go to the right, they get higher. As you go up, they get higher. So when we come over here, I'm just going to cross this off. Noble gases have no electronegativity. And here is the highest. And down here is the lowest. So if you go this way, it increases. In fact, I'm going to make this, I'm going to make this, as you go that way, they increase in electronegativity. And the higher you are, the higher, I don't know, you can do arrows, whatever, but the closer you are to fluorine, the higher the electronegativity. So, describe periodic trend for electronegativity. Highest, and that is the ability to attract electrons. Lowest, metals are throwing electrons away. How does this relate to bonding? So if we've got a compound like, let's say, hydrogen chloride, hydrochloric acid, Well, let's see what type of molecule. Well, first off, these are two nonmetals, so we know this is probably going to be a covalent bond. But let's see how covalent it is. The electronegativity for hydrogen is 2.1. 2.1 for, make sure we see that, chlorine. So hydrogen's a penguin, chlorine is the polar bear, 3.0. 3.0. We subtract those two numbers. I believe we get we get 2.1 is 0.9. So now we subtract that number. You look on this chart, 0.9 is going to be moderately polar covalent, 0.9. So it's moderately polar. Polar means it has a plus or minus side. Look at there, HCl, it tells us right there. So electronegativities help us predict whether the compound is, this will be partially negative and this will be partially positive, and it tells us how strong. This is probably an adult penguin and a baby polar bear, because there's a little more sharing going on than there would be if this was hydrogen fluoride, which would be the biggest of the polar bears, hogging most of that. And I think with fluorine, if we were to do that, we would have 4 minus 2.1, which I think comes out to be 1.9. Is that right? 1.9. Yeah. And that ends up being, whoa, an ionic compound. Okay. So, okay. I'm done. Goodbye.